So, good afternoon, everybody, all participants. Welcome back. We are here with the keynote session 5, and we are going to begin the session right now. We have with us our session chair, Dr. Debashis Day from MAKAUT West Bengal, and also Dr. Abhishek Das from Aliah University. Sir, Abhishek sir, it is over to you. You may introduce our speaker of the day.
Yes, Abhishek. Yes. Thank you. Thank you, Tufan.
Thank you, Tufan. It's indeed a pleasure to introduce the keynote speaker, Professor Dr. Bart Preneel from Leuven University, Belgium. In fact, I've been to Belgium once in 2011, and I really love the chocolates there. They're wonderful, and the people are very nice. So Professor Bart Preneel is a full professor at the KU Leuven. He heads the COSIC research group, which has 100 members. He was visiting professor at 5 universities in Europe. He has authored more than 400 scientific publications and is inventor of 5 patents. His main research interests are cryptography, information security, and privacy. He is a designer of the hash function RIPEMD 160 that is used in Bitcoin. As you know, Bitcoin is very popular these days. Bart Preneel has served as president of the IACR, International Association of Cryptologic Research, and is co-founder and chairman of the board of the Cybersecurity Cluster LSEC. He is a member of the stakeholders group of ENISA, that is European Agency for Cybersecurity, and of the Academia Europea. He has been invited speaker at more than 140 conferences in 50 countries. He received the RSA Award for Excellence in the Field of Mathematics in 2014, the IFIP TC11 Christian Beckman Award 2015, and the ESORIX Outstanding Research Award 2017. In 2015, he was elected as Fellow of the IACR. He frequently consults for industry and governments about security and privacy technologies. He is also the co-founder and board member of the startup NextAuth and member of the advisory board of Tioga Capital Partners and Neem Technologies. So over to you, Professor Bart Preneel, and his title of the day will be Blockchain Challenges and Opportunities. Sir.
Welcome, Professor Bart. Welcome. 1 second.
Thank you. And thank you, Dr. Das, for the nice introduction. And I wish I could be in Kolkata today, but unfortunately I cannot come back. I've been to India many times and I always enjoy it. So just to give you an idea where I am now, I'm actually in my university office, and this is the view from my office. I can look at the castle. It's very cold though, it's 6 degrees, but we have a little bit of sunshine today. And so I hope it's useful to see where I am now, but I really wish I would have been with you in Kolkata. So today I will just give a very brief background because this is a blockchain conference and I think most of you know the basics, but I just situate the context. I will discuss the debate on consensus mechanisms on blockchain. This is a very hot topic and I'll try to give you a perspective on this. And then as cryptographer, I want to say something about the impact of quantum computers and post-quantum blockchains as a consequence of this. And then as a third part on the menu, something completely different. I want to talk to some work of my students on the layer 2 protocols for instant payment. That's more or less the menu. So just to remind you, this is a slide I really like very much from George Genesis. So if we do blockchain either for cryptocurrencies or for other applications, it's really about memory. We want to actually preserve something for the future. We want to actually keep record of transactions. And as you see, 5,000 years ago, there was systems for payment based on stones, where every small stone represented an animal, and you could put them together in the bigger stone, and then you had a flock. And this was a decentralized system, which is corresponding to for example, coins or notes. While in the middle, you have this bookkeeping system, a centralized system where the central rulers kept track of the debt of the individual underlings of their empire. And so two very different systems, a centralized system with a centralized ledger in the middle, and then on the left, it's a more decentralized system. And as you see, we still have this debate 5,000 years later. What is amazing is that we can still read and understand these things. Well, we can wonder what's going to happen in 5,000 years with the systems we are creating right now. But at least the goal is clear. We should actually long-term preserve what is happening and make sure we actually keep record of everything that's happening. And so the anthropologist David Graeber wrote a very interesting book. So he argued that money was invented to keep track of debt. And so his book is called The First 5,000 Years of Debt. So very interesting perspective to understand what we try to achieve. So when we speak of blockchain, we always speak of consensus mechanisms. So maybe it's good to go back to the history of that field. So this problem was first formulated in 1978. So I guess you all understand that in 50s and 60s, we had mainframe computers. And then in the 70s, computers started shrinking. The IBM PC would only come in the early 80s. But at least people realized there would be multiple computers and would be talking to each other. And then the question is, how do you maintain consistency between the information on those computers? So this is a very important problem, also a problem we try to resolve today with our blockchain protocols. And so this problem was reformulated as the Byzantine general problem at that time. So the model is you have a number of generals around Byzantium and they have to achieve consensus on when to attack. If they can achieve consensus, then they will of course win because they will overpower the defender. But if they don't achieve consensus, they attack at different times and the defender can defeat them one by one. Now this seems like an easy problem, but of course the Byzantine generals did not have a smartphone to call each other and to just agree on a time, or they couldn't use WhatsApp or something similar. So they actually had to send messages to each other, and these messages could get lost. So these messages could be intercepted, so they were unreliable, so the communication was unreliable. And also some of the generals themselves could actually be traitors, could be corrupt, or could be collaborate with the city under attack. And so the question is, can we actually get consensus? And the answer was, well, it depends, of course, on the communication model, asynchronous, partially synchronous, synchronous. I'm not going to go into detail. But more or less the message is that it's possible to achieve consensus among the honest generals if the number of traitors is at most 1/3. And this is known as BFT, so the Byzantine problem. But also very important to note is that there was no way known until 2008 to achieve consensus if the number of generals was not known in advance. And so this is actually the problem that was solved by Bitcoin. So Bitcoin managed to solve this problem in a paper that's very unacademic, very informal, but actually very innovative, because this problem that has kept researchers busy for decades, eventually after 30 years was solved by using a completely innovative technique, namely proof of work, and we'll come back to that. But by itself, the technologies underlying Bitcoin actually are amazing, simple and easy to explain. And for cryptographers, they're more or less the bread and butter, very simple techniques. So what we need are one-way functions. They were first proposed in the 70s for protecting passwords, and then later for hash functions for signatures. And then digital signatures themselves, concept put forward by Diffie and Hellman in the mid-70s. Then we have Merkle trees put forward by Merkle in the late 70s. This is a way to authenticate a huge number of values in the case of blockchain, all the transactions. And you do this by hashing them in a tree structure and actually only protecting the root. And it's quite easy to also prove membership in such a structure. So this is all 70s. Then in around 1990, people had the idea of linking transactions to a hash chain, where you would hash transactions into Merkle trees and then chain those trees, and then intermediately publish these values, the values in between. For example, the company Shruti Technologies publishes this value of the hash chain in the New York Times since 1994 in the weekend. So you can still every weekend buy New York Times and get actually this hash chain from this company that does timestamping service. This is an idea of 1990, and the company was created in 1994. So well before Bitcoin was invented, or the concept of blockchain was known. It was not called the blockchain, it was called the hash chain. And then in 93, Dwork and Naor proposed the idea of puzzles. So let's have proof of work. So a proof of work is a cryptographic puzzle, which has two properties. It should be hard to solve the puzzle, But once you have a solution, it should be easy to check the solution. And so the puzzle that we now use today in proof of work is we take a hash function, and the output of such a hash function is a random string. And the requirement is we should find a string that starts with many 0 bits. And at the time being, in the Bitcoin system, these puzzles are very, very difficult. The number of 0 bits that you have to achieve is 80, which means you have to do on average 2 to the 80 attempts of different inputs to actually solve the puzzle. But the nice thing of this puzzle is that once we have a solution, it's very efficient for anybody to just apply the hash function to the solution and to check that indeed the result starts with 80 0 bits. So it's hard to solve, but easy to check. And so more or less, amazingly, these 5 simple building blocks that were all known since the early 90s were used by Satoshi Nakamoto to solve the business in general problem, which was open since 1978. Well, the difference was with the earlier solution that he could solve it for an arbitrary number of channels. So the number of channels had not to be known, the number of actors had not to be known in advance. So he created an open system where anybody could join. There was no permission delivered to join or not join the system. Anybody could actually set up a node and become part of the system. So as I mentioned, the solution of Satoshi Nakamoto, in which he proposed for the Bitcoin currency, was proof of work, where you actually solve a very difficult puzzle. And this puzzle actually initially was quite easy, but the goal of the Bitcoin system is that the puzzle is solved every 10 minutes. Every 10 minutes, a new block is created. So if more and more people try to solve the puzzle will be solved faster. And to prevent this, the puzzle is every 2 weeks made more or less difficult, in general more difficult. So every time if the puzzle on average takes less than 10 minutes to solve, then the puzzle will be made harder. And so this is why after 13 years, we now end up with a very challenging puzzle with about 80 0 bits to solve. Now, what kind of function do you put? Well, some cryptocurrencies actually put, like Bitcoin, put SHA-2 there. And the consequence is that then people start building ASIC specific chips to actually do the hashing. And because they're more efficient at this than any CPU or GPU or even FPGA, because these ASICs are specifically designed to do hashing. Now, this means, in fact, that you will get concentration of power, that people who have the budget to produce ASICs or to buy a large number of them, they can do mining or they can solve these puzzles much better than the average user. So people try to get around this by designing memory hard functions, which means that you try to make a function that is hard to optimize by adding or using ASICs. And the idea of those functions is that you require a large memory, to be the memory of a normal computer, so something like a couple of gigabytes of RAM. And that actually this function reads at random to this hardware, so that your cache network or your cache is not very efficient, and that you really rely on the slow access to memory, which is about 100 times slower than the access to the cache memory. And so if you design your function like this, then it will be much harder or much less efficient for those who build ASICs or those who actually build large farms to solve this puzzle, because they have to use the same computers that you and I use in our desktops, and they will not gain much. So this is more democratic. But of course, what you then get is then people write malware, and this malware spreads via the web or via malicious apps, and then actually mines on everybody's computers. And of course, doesn't give the benefits and solutions to the user themselves, but to the hacker who controls the malware. So it's we're kind of between a rock and a hard place. I'll say a few more things about proof of work. Next, then there is another alternative being considered, is proof of storage. So the idea is there that you don't solve a puzzle by doing a tough computation, but actually you store data. And the assumption is everybody has actually free memory on their drive somewhere. Most of us do have some drive with free memory. Why don't you store stuff there it can be used to solve a puzzle? And if you store more, you have more chance to solve the puzzle. So this was first explored in Spacemint, and then a more clever idea, or more elaborate idea was Kia, that actually was published 2 years ago at AsiaCrypt. And so a Kia cryptocurrency went live. One of the problems seems to be that actually, yes, this storage is available, but actually the current hard disks are not very suitable for regular rewriting and regular reading at random places. And so it turns out that, at least that's what you can see, is that these solid state hard disks that are very fast and very suitable for this purpose actually wear out very quickly. So in fact, it's not free storage, you actually destroy your storage. So there is some risks there. So people then propose the idea of, why should we solve a puzzle? Why can we actually not let those who have currency or a stake in the network make decisions? This is known as proof of stake. We'll come up in more detail. But then there is also other ideas. For example, Intel says, well, we have trusted computing. We have something like an SGX unit. And so we can actually trust this computer to arbitrate and be fair, and in this case to create a delay, so we can prove that we have waited for a certain time, because nobody can clock this above a certain speed, and we can actually check this. And so this is another alternative, a clever idea, but of course now you have to trust Intel not to cheat, because Intel of course could also build other hardware that actually would cheat this proof. There is many more consensus mechanisms, and if you want to read more, there is an article published earlier this year in IEEE Access that lists no less than 130 different consensus protocols, all based on many different ideas. Of course, there is still the older line of research that still continues, and of course gets renewed interest, which is the Byzantine general problem. So this is a setting where the Byzantine fault tolerance, where you know the number of players in advance, so you don't have an open system, but there is somewhere a central party. We call this very often a permission blockchain. There is a central party that decides who can join the system. And this party, of course, knows how many players there are. And so these general problems, I didn't elaborate how this is being solved, but typically they're solved with voting procedures. And so, of course, stimulated by the developments in Bitcoin and blockchain in the last 10 years, there has been an enormous interest in further improving, extending these protocols. And so there is also quite some systems that work on Byzantine fault tolerance, so more ideas of the 80s that are now being optimized in view of lessons we've learned, and in view, of course, also of the increasing interest in solving the problem. So the main message is that there is many consensus mechanisms. It would be very easy to actually give a whole course of 20 or 40 hours just on consensus mechanisms and how to deal with them. In general, they're very tricky to design, and they're very also tricky to analyze, and also very tricky to actually prove that they satisfy certain properties. And so progress there, I would say, is rather slow, but we are making progress, and we're getting better at understanding these complex problems. So that's what we do in the academic world. But of course, now after this cryptocurrency crazy developments happening, of course, the reality is not always waiting for the proofs, and people have rolled out more than 10,000 cryptocurrencies that all use different kind of consensus mechanisms. They all claim that their mechanism is better, so it's quite chaotic world out there. And I don't have time to completely describe it to you. I think it's probably too early still. The dust still has to settle, and there is still many difficult open problems in trying to understand those better, and try to understand better which ones correspond to reality. Because of course, there is a lot of ad hoc schemes where people say, trust my consensus mechanism because I know how to do it, and I'm a very competent person, and I have very good code. Then there is the academic approach where we say, well, we have a model here, and in this model, we can prove certain properties about our consensus mechanism. The question then is, of course, how well does this model reflect reality? How well do your assumptions you make, do they reflect their assumptions in the real world? Assumptions on attacks on the network, assumptions on synchronous or asynchronous or partially synchronous. How realistic is this? Are people trying to attack your network rational or not? So there is all these kind of questions that are very difficult to answer and that depend on the context where you apply the mechanism itself. So I will not give you an extensive lecture on consensus mechanisms, but I'll just highlight a few of the properties of proof of work and proof of stake and try to understand why these two things are different, and why there is actually a debate between, I would say, two factions that believe in one or the other. So the main proponents of proof of work say, well, proof of work represents actually a mechanism where you have something else, some physical process. So in this case, burning of energy to perform computations. And this is used to stabilize a network or to get consensus. So they say there is, on the one hand, there is a network of computers that want to achieve consensus. Anybody can join, so it's a very open network. It also is likely to be unstable or unreliable. And to make this stable, we have to rely on a physical resource that's limited. And this physical resource is computation, which in practice boils down to silicon, so chips, ASICs, and power, energy. So we see that these miners who solve these puzzles, they actually move there where energy is cheap. So they were largely concentrated, for example, in China, but then China banned mining. And so then they moved to Iceland, where electricity is cheaply available and also cooling is not a problem. We also saw some migrations to Iran and to Texas, also places where energy is cheap. So this is the point I wanted to make, of course, that mining for those cryptocurrencies, because now large amounts of money are involved, they're no longer done on CPUs or GPUs, or not even FPGAs as in the first years, but they're now done on ASIC farms. So these are just hangars full of racks or rows of racks, and all these racks are full of ASICs. And all these ASICs, in the case of Bitcoin, they only try to find inputs that hash to a value starting with many 0 bits. For humanity, this is a very useless computation, but of course it serves to stabilize the Bitcoin ecosystem. I don't recommend you to start mining yourself, but if in case you would want to, you can actually buy this equipment. You can buy those ASICs on Amazon, and it would be very interesting to study how actually the price varies with the Bitcoin price. So what you see here is a slide from I made 2017, so a bit more than 4 years ago. At that moment, the most high-end miner was the Antminer S9. It cost about $2,300, and it could do 14 terahashes per second. So 14 terahash is 14,000 gigahash. So it's 14,000 billion hashes per second. And this uses 60 nanometer technology. So, and this mining, then when the Bitcoin price went up, the price of this miner went up. So of course, the silicon was still the same, but the profits increased because the price of such a miner is not derived from the silicon cost, but from how much money you can make with it. And as you saw a year later, actually, there were probably better miners available and the Bitcoin price was a bit lower. So in fact, these miners became cheaper. Now I looked also at most recent models. So 3 months ago, you could buy the Antminer S19. And as you see, it's now 110 terahashes per second. So about 8 times faster than the previous one. The price is also substantially higher, $17,000, I guess, because of the new model. And it also has become about 10 times more energy efficient. So you will reduce your power bill substantially. And this is 5 nanometer technology. So it's a very high end of what we can do in silicon today. So all these miners solve this puzzle. As I mentioned, this puzzle in Bitcoin is taking some inputs to a hash function related, of course, to the transactions and to the previous value of the blockchain, and solve this puzzle. We don't actually know how much power is being used to solve this puzzle. Of course, we know how difficult the puzzle is, and we know how many computations have to be done on average to solve the puzzle, but we don't know who solves the puzzle because these people are anonymous. They will also not tell us which ASICs they're using or how much they pay for their power, or even where their devices are, because in the past, people have stolen these kind of farms. So it's not very smart to announce or explain where your farm is or what it does, because it's a competitive space. But of course, you can make some assumptions based on, for example, the price on Amazon of certain mining equipment, and you can make assumptions on the price of electricity in certain countries. And so from this and from the puzzle solving in Bitcoin, you can make an estimate on how much power Bitcoin consumes. And so there is this website, The Economist, where this is being done. And so they claim that the energy consumption is something like 100 terawatt hours per year, which is a bit more than the energy consumption of Belgium, a small country with about 11 million people. This is an estimate. The lower bound, which is probably more reliable, is something like 40 terawatt hours. in addition, those chips, they can be used for a while, for a few years, but then they become useless because they're too slow and there is better ones available. So one transaction is estimated to result in 300 grams of electronic waste. So it's kind of a challenge that this system, this ecosystem, in this case of Bitcoin, which is the first widely used cryptocurrency, the one proposed by Nakamoto and has survived since 2008, is actually highly innovative in terms of energy, in particular because what Bitcoin does is something like 3 or 4 transactions per second. And this should be put in perspective. If you look at other payment systems, Visa has a peak capacity of 56,000 transactions per second. Alipay, a Chinese payment network, has a capacity of 256,000 per second. And Western Union, I guess maybe also widely known, has a capacity of 750 per second. So in fact, the cost of energy cost per transaction is very high, or we actually have to have a system that consumes about the same amount of energy as Belgium or even more, that can only do a handful of transactions per second. And the interesting design of the Bitcoin system means that it would be very hard with the current parameters, without changing it, to go above 10 transactions per second. There is, of course, many ideas to speed this up, and there is a lot of academic research there. And I think there is some ideas that can gain more by changing the protocol. But of course, it's always a tricky thing, because if you make the network faster, you actually risk more instability and you have more risks of lack of consensus in the network. Because don't forget, this is a network anybody can join. And all these nodes, at this moment, there is 10,000 nodes spread over the whole world. They actually has to achieve consensus. So inherently, there is some bottlenecks related to communications and related to delays to actually achieve a much higher number of transactions. So it's obvious that if you want to use this for retail payments, where people are really going to pay things, this is about 10,000 times too slow. So we have to have better ideas. Of course, Bitcoin may still be a useful way to do transactions at a slower rate for a slightly larger amount, where not everything has to happen instantaneously. In Bitcoin, a transaction takes 10 minutes before it goes to the next block at least. And then the advice is to wait 1 hour before your transaction is stable. So this is not something suitable to buy a coffee or even to buy lunch or dinner. But it does have its value if you want to make payments independent of any centralized party. But I guess that shows where the research drives us. Can we build such a system? So on the one hand, Bitcoin is a fantastic system because it solves the open problem the computer scientists were looking at for 30 years. Namely, can we achieve distributed consensus in a setting where the number of players is not known in advance? So it solved this problem. On the other hand, the transaction rate is quite limited, and the energy consumption is huge. So can we improve the system? And so some people believe they can do it by making small improvements to Bitcoin. And of course, also the other question is, does Bitcoin actually work? And so there has been in the last 5 years quite some interesting research that actually formalizes the consensus model, so uses the theory developed for Byzantine fault tolerance and extends it to settings like Bitcoin. So for example, can you prove that the chain keeps growing, that the system will not stop growing? Can you make sure that the fraction of blocks mined by the miners that are honest, that comply with the protocol, is actually large enough? So can you actually prevent malicious miners from inserting malicious blocks or malicious transactions into the network? Does everybody agree? So is there a common prefix? There is always some debate about or doubt about the last blocks, but is there actually an agreement among all the players that we actually have a common prefix? Can we actually agree together on the state of the network? And then liveliness, can we censor transactions or not? Or is it always possible to let one transaction go through? So of course, I give here only informal definitions. If you want to have a formal analysis, you have to formally define what this means. And then there is long and complex papers that actually prove that certain properties are satisfied, like, for example, this kind of theorem, which I just took from the paper by Paz et al. 2017. I'm not going to read the theorem in detail, but you can look at it. It actually proves consistency, chain growth rate, and chain quality with certain quantitative parameters. But this is actually very nice because it gives us a better understanding about this protocol and why it achieves its goals. But of course, we have to be very careful. This is a proof in the round cow model. So if a cow is round, then we can prove these things, although we all know in practice that cows are not round. So this is an idealized assumption. And the big question is, what happens if we don't comply with those assumptions? And so, for example, what if miners are malicious and don't publish the blocks they find, but they actually wait and they actually mine in secret and they only publish after a while? So, for example, these kind of things, or what if somebody would bribe a miner to misbehave? So miners have to make big investments so they may not misbehave, but what if I can rent their equipment and misbehave for a short time? And so these things are not covered by this model. So there have been quite some attempts. So as soon as Bitcoin became popular, say 2014, 15, in subsequent years, to actually improve Bitcoin and try to improve the Nakamoto consensus to actually get more robustness or to get a higher number of transactions or to get a better resistance against malicious behavior. And some work one of my bright PhD students did, Ren Zhang, who is now working at Nervos, which is a cryptocurrency organization in China. He actually did a detailed analysis of all these improvements of Bitcoin and small tweaks. And amazingly, most of those improvements, quote unquote, do improve something, but make something else worse. So he developed a framework to actually study whether these small tweaks or improvements to the Bitcoin consensus mechanism actually discourage selfish mining, so dishonest behavior of miners, or whether they actually stop double spending, or whether they make it easier or harder to censor other transactions, so to prevent somebody from making a payment. And so the bottom line is that all these improvements that were proposed turn out to be indeed an improvement in one area, but actually then you pay a price in another area. And so overall, it's not clear that any of these improvements really makes a better system, which is kind of amazing because so this one guy who proposed Bitcoin actually seemed to have had very good intuition, and it seems to be very difficult to improve over what he did. Of course, we can make small improvements and small gains, but it's not, if you look at the global optimization, it seems to be very hard to do very much better. So very quickly after Bitcoin became more or less established, because in the first years in 2009, Bitcoin had some very difficult years, but then it started getting better and better. And then very quickly on a mailing list, somebody suggested to do something better than proof of work and to move to proof of stake. So the first message to this was actually in the very early days, was in a forum in 2011. And so the idea is the following, that you have a cryptocurrency system, and if you own some coins in the system, you stake those coins, which means you actually kind of commit to not move them and to keep them. And then these coins become lottery tickets in a lottery. And so what miners do is they actually don't solve hard puzzles, but easy puzzles based on the information of the stakes, the number of the round, and some public randomness. And so in fact, more or less, you can say that there is a lottery, and the person who wins the lottery, so lottery is among the staked coins, the person who owns coins and who staked his coins and who wins the lottery can decide on what the next valid block is and can actually move forward. So instead of having very hard puzzles, it's a very easy puzzle. You just have to check whether or not you won the lottery with your stake. Of course, this assumes that those people who stake their coins are available online, right? Because otherwise they can't play part. And if they don't play part, then these coins are not being used. And then, of course, the network can perhaps take over the network. So it requires some commitments of people who own coins. A substantial part of them have to become miners. So this is believed to be more scalable because, of course, there is still bottlenecks in networking, but somehow we don't have to solve this enormously difficult puzzles. We don't have to consume these hundred of terawatt hours. It's much more efficient at the cost of making sure that there is enough people who own coins to be online and to be available to actually participate in the voting on what the next block will be, or in the lottery to decide on the next block. The idea with 2011, it actually took off very quickly. So Peercoin still exists today, was a kind of hybrid between proof of stake and proof of work. And then a whole other series of protocols was put forward and rolled out. So maybe remarkable is that Ethereum is kind of the, I would say, the second big cryptocurrency after Bitcoin, because Ethereum made some improvements. So it uses a slightly different proof of work puzzle. So it decided to use a slow hash function, so the ones that are less efficient on ASICs. And Ethereum also has more complex features than Bitcoin. So while Bitcoin, you can only do transactions, in Ethereum, you can actually compute any code. You can achieve consensus on any code being computed for being evaluated over all the nodes. This is called smart contracts. And so Ethereum had a plan to move to proof of stake, but of course they first had to be sure it would work. And so they decided to choose for Casper FFG as the proof of stake protocol, but as far as I know, they still haven't deployed this, so this is still happening or on the schedule for the coming years. So the other interesting one is Cardano. This is the currency is called ADA after the famous computer scientist. And so Cardano is based on the Ouroboros protocol by Aliah and others. So this is actually a protocol where there is some scientific research behind it. The other ones are like Bitcoin, that people think about something, very smart people, and they make a proposal and then they let it run. But in fact, there is no formal analysis. As you remember, also for Bitcoin, the first papers analyzing Bitcoin and studying the model were only in 2015 and 16. So this is 7 or 8 years after the system was proposed. So we saw something similar in the proof of stake. There was a lot of deployment, but the academic research came actually also later. So again, so the idea is more a lottery among those who have stake in the network. And there is a cryptographic ID there. What you do is a verifiable random function. So it's a function that you can evaluate that produces a random output, but anybody can verify that the computation is correct. And so there has the first series of protocols there is Sleepy and Ouroboros variants. Ouroboros Genesis is a more complex variant that allows to extend the number of players. So Ouroboros Praos actually assumes that you know how many players there are in the system. And then there is other systems like Snow White and Bulgaria et al. Also propose the system. So these are the systems that follow more the Bitcoin style, which means that your system progresses block by block, or I should be more precise and say epoch by epoch. And there is also a system that have a more complex consensus mechanism where there is multiple rounds of communication. I think the best one known is Algorand, but of course the oldest one was Ouroboros. And then there is also EOS and Definity. Definity is quite famous because a large number of cryptographers in Europe decided to move to Definity to work on their protocols. And this actually been noticed almost all through Europe because they hired so many bright cryptographers. And so more recently, a team led by Jonathan Katz actually proposed a block by block protocol because it turns out that the proof of stake protocols that actually are formally analyzed work on epoch basis, so multiple blocks. But so they managed to build a system that actually worked on a block by block basis for the analysis. And so the advantage of those schemes is that there is a mathematical analysis, there is a formal model, a mathematical analysis about whether the system is stable or not and secure or not. But so as you see, as some of those systems are being deployed in widely used coins, but there is no one-to-one mapping. Some of the widely used coins have no model behind them, just have a white paper with some intuition. And some other people have written very nice papers describing a system, but they've never actually deployed it and tested it in practice. But so a substantial number of cryptocurrencies are with proof of stake. And so as you see, Polkadot is the biggest one, is about $10 billion staked. ADA, so Cardano system, has about $8 billion staked. So overall, there is about, this is beginning of this year, there was about $45 billion staked in those proof of stake crypto systems or cryptocurrencies. This is still kind of small compared to the overall market cap of the cryptocurrencies, which is about 2,460 billion. So what you see on the left is that this is the top 12, but so you can actually go to this website and look at the 12,000 or 13,000 others. So from the top 10, the ones with the largest market cap. So as we see, this is the largest one, is the smallest one of those lists is Dogecoin, which actually is kind of hammered up as a joke. It was really like a joke of somebody who tried something. And then after a while, he actually thought the joke had lasted long enough and he sold all his currencies and he just had enough to buy a car. And so his currency now has a market cap of $26 billion. So I guess he wished he hadn't bought that car and stuck onto his Dogecoin. So what's interesting from a scientific point of view, so there is of those 10, there is 3 that actually are proof of work based. And the second one, Ethereum, has announced already for a while it will move to proof of stake. So Solana, Cardano, and Polkadot are also proof of stake. So it seems that proof of stake is taking over. And there is also 2 that actually work based on result in fault tolerance. So they still use, I would say, the evolved protocols of the 80s. And so this means there are more restrictions on who can join the system. And then there is also Tether as a user consensus protocol, and there's USD coin. Both are stable coins, which means that they peg their value to the US dollar. And they use, in case of US dollar coin, they use multi-chain, so they actually hook up to multiple chains. But so the message, I think the summary is, in the academic world, there is still a debate whether we can improve proof of work to make it more efficient. But it seems that there is a problem with the energy consumption. Proof of stake, there is active research and we seem to be making progress. But it's unclear what is winning in the field, but it seems that proof of stake is making progress, and maybe the climate change challenge may help there to push out or at least reduce a fraction of proof of work currencies. By the way, to give you a perspective, total value of all gold is about $11 trillion, or $11,000 billion. Total value of the stock market is about $95,000 trillion. So in that sense, these cryptocurrencies, of course, it's a lot of money, $2,000 billion. But in the overall picture of things, this is still kind of small compared to the stock market, is about 3%. So, but there is this big debate of proof of work versus proof of stake. And it's very interesting because people write very animated blog posts to prove that the other side is wrong. And so more or less the proof of work argument is that you can't stabilize such a system, especially not if the number of players is not known in advance. It's inherently impossible, let's say. We have to rely on some outside resort which is based on power consumption. If we don't have this, we'll not be able to make it. Proof of stake people say to the proof of work people, you're ruining the planet, you're consuming hundreds of terawatt hours of electricity. We think we can solve the problem without external resources, and what you're doing is ruining the planet. We have to stop you, and we have to show it actually can be done better. So fascinating debate. And so I guess in the end, it's unclear whether this debate will be solved in academia, whether academics can actually prove some of these things. We can increase our insights. But of course, in the meantime, they are being fought out in the field as well with real-life cryptocurrencies. So on the left, you see attacks that apply to all of them. So it's very important to understand that if somebody acquires 51% of mining capacity, or some even argue it less is also okay, you can shut down, of course, any proof of work. So say if the US government would decide that they would start building a large farm of crypto miners, which is just bigger than any mining equipment anybody else has, so that actually takes a majority, it would be very easy for them to solve all the puzzles, take all the Bitcoins and shut down the system. The question, of course, is given the amount of money invested in this mining capacity, is the US government interested in spending a large amount of money, probably more than $1 billion just to do this? With the risk that then a new ecosystem pops up after a while. The same thing happens, of course, in proof of stake. If you just buy the currency, then you own the stake and then you can take it over and you can do what you want. The second thing is that if you read the motivation of the Bitcoin paper, the motivation of Nakamoto was a distributed system where everybody had equal power, so kind of a libertarian view of the world where the government should not have too much power. Now, if you look at what happens in practice, there is this website, iWeDecentralize.com, and you look at some of the more popular cryptocurrencies, it turns out that in most of the cases, in fact, the control, either in proof of stake or proof of work, is in the hands of a small number of players, sometimes 1, 2, 3, 4. In a few rare cases, it's 45. But so in fact, we have already seen enormous concentration of power. So which means that more or less de facto, already 1 or 2 parties can take over the network and can actually do what they want, which means they can also take all the money or they can destroy the consensus. So I think it's interesting to see that this dream of creating a cryptocurrency where there was no central bank, but the citizens would all have control, this dream has somehow fallen into the water, because it seems that actually it's what happens in those ecosystems is that we end up with oligopolies and few players. Maybe the analogy in economics is what happened in the Soviet Union when the Soviet Union collapsed. What happened there also is that people were given shares of some factories, but then it turns out that very quickly some very clever people started buying those shares, and after a very short time, suddenly those factories were in the hands of very few people as well. Although in the beginning you give every citizen a share, it turns out that economics make it such like this that you get power concentration. So all these cryptocurrencies are vulnerable to attack on the infrastructure. If, say, a government or a hacker, large-scale hacker, would like to bring down all these servers, it's unclear whether they actually would survive it. If it would be a sustained long-term attack trying to flood things, I think many of the cryptocurrencies would fold. Of course, the bigger ones have more protection, but in general, I don't think so far they've invested very hard in this, and especially at the lower end of the tail, these things are probably easy to shut down. So specific for proof of stake is what's called the long range attack. So what stops me from starting at the same begin block, and maybe you generate a new block every minute or every 10 seconds, I can just generate a new block every millisecond. So I can catch up with you and create my own version of the system in which I own all the money. And so the argument of the proof of work people is, well, in proof of stake, there is nothing to prevent this kind of thing. And so you need some external force to do this. In the proof of work, it's energy cost. You will need some governance system to decide that this is the good guy, the good chain, and this is the bad chain. How will you actually separate such a new quickly grown chain, or you will identify it from one that has been following the rules and that has been generated much slower? So more or less, the argument is if there is no common clock, or people can speed up the clock, they can actually kill your system. And then the other problem is that if you're in a proof of stake system, you're shown 2 possible evolutions of the chain, nothing may stop you from voting for both. Of course, what you do like this is you kind of ruin consensus, you create chaos in the system, actually the system may not come to a decision, but in fact, you yourself may only stand to gain by voting on 2 blocks. So this is not clear why people don't do this more. The defense argument there is, well, it's not so easy to do this, in the holds for both cases on the left for proof of work and proof of stake. It's not so easy to build all those ASICs or to actually acquire, say, 50% or 35% of Cardano or of Solana. This is kind of hard. You would, first, because you need a lot of money, and second, it's not clear people are willing to sell to you. And then the second argument that's also used by both is, well, if somebody starts attacking the cryptocurrency, they first have to buy it, they have to be part of the ecosystem, which means they have invested in it, and then that actually will result in a price drop. So in fact, you would destroy the system, you would destroy the things you have in your own hands. Of course, there is in economy techniques like shorting things where you may be able to benefit from a price drop without being a victim, but I guess this is still not fully understood. So these 2 arguments that work for both proof of work and proof of stake, they're actually very valuable arguments, but they're not formal proofs that something will not happen. They're just, I would say, sociological observations with some economic motivation, but they're not formal game theoretic or cryptographic formal analysis of why this is not happening. The proof of stake people say, well, we also have a better alignment between different players, because in this proof of work setting, you have miners who have invested in ASICs, you have the maintainers of the system, you have the owners of the currency, And then you have the exchanges who facilitate exchanges. So, and those may actually all have slightly different interests, in particular miners and owners may have slightly different views on things. So miners of Bitcoin and owners of Bitcoin, while in a proof of stake system, the validators are owners, so you have less players, or the players are more aligned and things may work better. Again, this is a psychological argument. This is not an argument that you can use in a computer science paper, but there is of course something to be said for this. And so the other argument is that in fact, double spending attacks require large transaction volumes in proof of stake. And so this may be the reason why it's very hard to make them to happen. But so as you see, you can read blog posts or papers in which proponents of either side actually will strongly defend their own approach and attack the other approach. But I would say the jury is still out on this. On the ground, we see indeed that proof of stake currencies are making progress, but whether they will be stable is, I think, another question. So very fascinating debate with a component of science and of course a component of economics and a component of psychology as well. So the second topic I want to discuss, I don't think I'm going to have time for our instant payment scheme, but that's okay, is of course that many governments and the financial industry doesn't like this kind of open systems. They want more closed systems. They don't like distributed control where anybody can join. They don't like the transparency that you have on most of those cryptocurrencies. They don't like the unclear governance with no clear management system behind it. And as you see, some of the more successful cryptocurrencies actually got a better governance than Bitcoin and a clearer management. And of course, economists hate uncontrolled money supply. So this is why in practice, many blockchain systems where you see that there is restrictions on who can read or verify or write. So of course, in first instance, you want to restrict writers. Second instance, verifiers, and maybe you also want to restrict who can read. And of course, if you move to non-monetary applications, for example, proving the origin of diamonds or tracking containers, so this is logistics sector, then you may have less problems with interfering with the power of the state. So this is more or less where blockchain is evolving. Although it's also clear that more and more governments are looking at issuing centrally banked digital currencies. There's experiments in China and also in Sweden, and also the European Central Bank is looking at this. So cryptocurrencies will exist for sure. I think it will be very hard to kill them. But in those countries where the open ones are being blocked, but also in the other ones, it's clear that also states will actually switch to centrally banked currencies and will offer this. So next to the normal rupee, you'll probably have in a few years also a digital rupee. And of course, there we have the same problems to deal with about transparency, about governance, and about consensus mechanisms. Of course, in that case, it's a central bank issuing. They can say, well, we decide who owns how many cryptocurrencies, but they may also delegate this to the banks, the commercial banks themselves, and then we need consensus algorithm on who owns how many between the banks. And so there, everything we learned so far in the open cryptocurrency world could be transferred to the more restricted cryptocurrency world. In this kind of setting, of course, it makes more sense to use built-in fault tolerance because they have a number of players will be restricted to either one player or centralized system, central bank, or the commercial banks, but then under a control system by the central bank. There are still many benefits to blockchain, and I will not go into detail because I'm quite sure others have spoken about this. I want to speak today about the cryptographic part and about post-quantum security. Maybe also about the business cases. I want to say one thing is that something we've learned, I think, from the last 5 years when blockchain became a hype is that we need to develop complex ecosystems where we have interoperability between different systems, where we have proper regulations and good business cases. And I think history has taught us that these kind of things require time. You cannot create those things overnight. It may take quite a long time to do this, but there is definitely value. So cryptographers warn others that you have to be very careful with cryptography because cryptography can get broken. In a good design, you can actually change your algorithms. But in most cryptocurrencies, it's not possible. And so to actually upgrade the algorithm, you want to have a hard fork, which means that all players in a system have to agree to use new cryptography. And this is not so easy, especially not in a kind of more decentralized or anarchistic managed network. If there is, of course, a central party making decisions on membership and permissioning things, they can also decide to change cryptography. But again, you have to convince everybody to do this. There is exceptions, like in the IBM Hyperledger Fabric, plugin consensus mechanisms can be used. And also, of course, in smart contracts, you write your own code and you can decide which crypto you want to use, but not for the blockchain itself. So an important threat to cryptography is the idea of quantum computers. They were coined by a Russian Yuri Mavin in 1980, and at the same time by Feynman in the US. And so the idea was, can we build computers that use the principles of quantum physics, which means that the bit is a superposition, or can be a superposition of 0 and 1. So in classical computing, a bit is 0 and 1. In physics, we have the concept of superposition, where some physical object like an atom or a photon can be in superposition of states, and only when you measure it, the outcome is there. And so they wanted to use this principle to build computers with exponential parallelism. And their main goal was to simulate physical processes. So they wanted to actually build computers that could be used to compute like in the same way as physical reality. And so after 10 years, people started building those things. The biggest one 20 years ago was a 7-bit computer in Stanford University. And this computer got famous because it was the first computer that did something useful, namely it factored 15 as 5 times 3. Because indeed, in the early 90s, 2 researchers, Peter Shor and Love Grover, actually showed that these quantum computers would also be useful to actually break cryptography, and more in particular, public key cryptography. And so the victims would be RSA, Diffie-Hellman, INZP, but also elliptic curves. So more or less, in public key cryptography, this is 99% of all commercial deployments. A number of devices, I estimate, is between 15 and 20 billion devices. With a quantum computer, you would be able to break all those schemes. For symmetric cryptography, Grover showed that you can speed up key search by a factor of 2, but it's not clear how practical this is. The algorithm that Shor proposes to factor in discrete log is actually an FFT, and is actually one of the easier algorithms to implement. Grover's algorithm has problems with parallelization and requires huge computers. So it's not clear at all it's such a big threat. But Shor's algorithm for public key cryptography is a major threat. And the large players are making progress. So I showed you the 7-bit computer 2001. Fast forward 16 years, IBM has a 50 qubit. And last month, IBM announced 127 qubits. And you see here their roadmap. So they promise more than 1,000 qubits by 2023. If you look at the details of that roadmap, they don't go further. They will, of course, you see other players are following them. So Google, Intel, also in China, players are going for bigger computers. So it seems to be quite plausible that we have a 1,000-bit computer in a couple of years. But how fast it will grow after that, it's unclear. Now, the good news is that to break RSA 2048, which is a widely used system today, you require about 4,000 qubits. But that's our ideal qubits. The qubits we can build today are noisy qubits, so you would probably need about 20 million of those. So in fact, we don't have to look when we can build a 1,000 qubit computer or 4,000 qubits, but actually a 20 million. And so this is probably still a way off. So when should you switch? This is known as Moscow's equation. So if there is Q years until the first large quantum computer, if it takes X years to switch, Y years for your data to be confidential, then you should switch in the year 2021 plus Q minus X minus Y. So this is the only equation I have on my slides today. I had also one on blockchain, but I didn't go to the detail, the Bitcoin system. But so plug in some numbers, Q15, X5, Y10, then you should actually switch today. For authentication, you actually can take Y small because you don't need long-term confidentiality. So researchers already started looking at alternatives. And so 5 years ago, NIST started a competition where they got 82 candidates. Many got broken. And so at this moment, actually, we only left with 6 schemes, more or less 2 lattice-based signature schemes, 3 lattice-based encryption schemes, and 1 code-based encryption scheme. That's more or less what is left. Plus now there is also kind of a hash-based signature scheme that is being reconsidered. But so the news is not so good. Well, we have now good candidates, but as you see, has been a very tough competition and very few are standing. And now what happened now is something we really didn't want to happen. CNRS has actually claimed that one of their patents covers 2 of the 3 remaining lattice-based schemes, which more or less would mean that for lattice encryption, we would only be left with 1 scheme, which is really not very good. So 1 lattice scheme and 1 code-based scheme. So how does this affect blockchain? Well, for the proof of work puzzle, there is no real problem, because if the computer solves the puzzle, then just make the puzzle harder until it takes 10 minutes. For transaction hashes, Merkle trees, and blockchain links, there is Grover algorithm that actually reduces per image search to the n/2 and collision to the n/3. But so Grover requires very hard constants in front of those order of magnitude. Asymptotic complexities is hard to parallelize and requires huge computers. So it's not clear even it presents a problem. SHA-2 physics still has ample security margin, and there is candidates available which are efficient. SHA-5 fails, SHA-3 which would stop this. So in fact, for the core of blockchain, there is no problem. There is a problem for the signatures, because we would have to replace ECDSA. So you would have to take the amount of currency attached to an old public key and sign it with a new private key and attach it to the new public key. So that doesn't have to happen 10 years in advance. We could do this a few years before the first quantum computer is built. But the problem, of course, is that those signature schemes, and here is a comparison from a recent paper. On the top, you see ECDSA, which is now used in Bitcoin. So you see hash-based signatures. The signature explodes in size, 16 or 17,000 bytes versus 73 bytes. Lattice-based schemes are slightly better, but still, again, a factor of 20 to 30. In fact, verifying becomes faster, signing becomes slower. But so it's not clear at all that this, well, it's clear that this will bring a performance hit for our blockchains, plus a huge expansion by a factor at least 20 of all our blockchains, which could be problematic. With the fancy crypto, we are actually even in more trouble because they use like ring signatures, morphic encryption, and pairings in Zcash. So sometimes we don't even have at this moment a post-quantum equivalence to this. So we have to be really doing quite some research to solve this. Some cryptocurrencies already were designed with post-quantum in mind, like QRL and Mokimo, and the others all say they're working on this, but remains to be seen. By the way, I don't give any advice on any of these currencies. So time to wrap up. So let's just go to the last slide, and I apologize for going slightly over time. So I do think that blockchain is an exciting technology for distributed consensus. We can now deal with open systems where anybody can join, but there is a lot of work to be done to establish whether proof of work or proof of stake is the best solution, or maybe still something else. So consensus algorithms are a very active area of research, and there is, as you saw, many proposals and many challenging open problems. The quantum challenge, so quantum computers can be a benefit to society, but they can also present a challenge because they actually require that blockchains are redesigned. There is no problem for the core blockchain because as hash functions, that's the easy part. And the challenge is mostly for the signatures and also for all the fancy features like everything that offers privacy or mixing. But so the interesting thing is that blockchains offer novel ways to use cryptography to achieve more robust systems. I'm going to stop here. Thank you very much for your attention.
Thank you, Professor Bart, for your excellent presentation. And you have covered a lot, starting from proof of work to proof of stake. And actually, I was also looking about the proof of elapsed time by Intel. Now that there is another very interesting thing. And you also talked about the quantum challenges, right? So I'm also working in the quantum computers. I use IBM Q to develop this model, some of the models in quantum computers. So yes, so I think people will develop this quantum challenges to mitigate this problem, right? So what is your suggestion? That you have mentioned that signature is the problem, right? Challenge is the signature part, digital signature part.
Well, it's not a challenge in terms of the hash-based signatures are very robust. I mean, we understand them, and I think there has been quite some progress. The ideas are from the 70s. I mean, Winternit's signatures, they're actually very simple ideas. But in protocols like XMSS and Sphinx, people have optimized things and improved things. So I think we understand them well and we can make them a bit better, but the problem is still this huge explosion, right? I mean, we go from a signature of less than 100 bytes to something like 60,000 bytes. And if you think of a transaction on a blockchain, this is several signatures. So currently the Bitcoin blockchain is 390 gigabytes. I mean, imagine you have to multiply this by 100. So we'll have to come up with different mechanisms because it's clear that this is not going to scale very well. So probably layer 2 protocols will have to play a role there, which means I didn't discuss them today, but that you have your blockchain for few transactions and for stability. And then for individual transactions, payments, or more smaller transactions, you actually use a layer 2 protocol where you do your payments. And then once in a while, you revert to the blockchain to reduce the number of transactions. But so I think the problem is indeed this blow up of signature size. I think the verification time, this is tolerable, or signing time that increases, that's tolerable. But I think the big problem is the size of signatures and public keys. And so for Lapis-based schemes, where there is some uncertainty still whether they actually will hold up, but we can hope they will, then we pay a factor 10 or 20 or 30, which is already huge. And there seems to be no way to solve this quickly. For signature size, it's even worse.
Okay.
And I guess the research problem is, can cryptographers find better signature schemes? I guess we should work on this as well. Can we make post-quantum schemes that actually are more compact?
So any question from the audience?
Professor Bart, I am Debashis. Hi.
Yeah.
So that is a very nice presentation, and hopefully hope that our participant will be enriched and they will get the new research directions on security and blockchain technology, and particularly security in blockchain.
I have one just query that you have talking about non-financial blockchain. So just like other than the cryptocurrency, so for example, IoT, it needs lightweight consensus theorem, right? So what is your suggestion? Proof of stake is fine or any other?
Well, in general, I'm very skeptical about the combination of IoT and blockchain, because people at this moment, IoT is 12 billion devices.
Yes.
Right. Even if each device writes a few hundred bytes every minute on the blockchain, you're going to end up with a huge storage. So you will have to somehow separate this. And so it seems that we already have a problem dealing with transactions on a blockchain of citizens, and we only have, say, 7 or 8 billion people. But I think in the next years, we'll have 30 or 40 billion devices on the IoT. So I'm kind of skeptical whether this will be scalable. So I think that for IoT devices, maybe at some kind of concentrator level, we can do this. But I think at individual devices, at least it's clear that on these devices, we never can store the blockchain, right? So that's just a simple back of the envelope calculation that on the IoT device, we can't store a blockchain because just there is no space.
Sir.
Yes. Yes. Thank you. Yes.
Hello,
Another
sir.
question. Yes.
Hello,
Is it
sir.
clear?
Yes, sir. Sir, thanks for your nice presentation. And we can be able to enhance our knowledge in the blockchain technology. Sir, I have one question in the non-financial fields of blockchain, that is for wireless sensor network. Suppose in the suppose for security purpose, for provide the security in the clustering protocol. Suppose I provide the security in the leech protocol using the concept of blockchain. In that case, I have found that suppose if I implement any consensus protocol, so if the existing all the consensus protocol, they need the high computational power. So in the census network has some limitations of the energy. Energy is the one of the constraint in the sensor network. So how this problem will be handled in that type of scenario?
Well, I think we should look at how we've been doing complex networks. We make them hierarchical and we trust some nodes. I think consensus networks, they assume that you don't trust anybody, or you don't know who's honest and who's fair. But
Yes,
I don't
yes.
think that this consensus networks, they're suitable for very tiny devices, because they indeed require quite some computation and communication overhead. So I think what you will have to do is probably have some intermediate nodes, hierarchical structure. Intermediate nodes, they talk to the center nodes. They don't know which ones are reliable or not, but they make a centralized decision. And maybe you'll have between larger clusters of these intermediate devices, you will have some consensus algorithm if needed, but I don't think you can implement it at level of sensor nodes. I mean, the same more or less applies to my answer to IoT. You cannot implement consensus between 50 billion devices. We can't even do it between 10,000 nodes on the blockchain. On Bitcoin, this is challenging. We can do it, but it requires enormous computational power and communication. You will never do this. This is 10,000 nodes. This is never going to scale to 50 billion nodes. So I don't think blockchain can be used at the node level, but maybe it can be used at the higher level of the hierarchy.
Okay. Especially in the vehicles, in a vehicular network, I have seen at least thousands of papers available. In vehicles, all the vehicles are as a node, as a blockchain, as a block. So, but I think you're saying that it's difficult. I understand also, but so maybe the RSUs, roadside units, can be connected to the blocks. Yes. Thank you, Professor Bart.
Well, also for privacy reasons, I would not want to do this, but
okay.
Thank you, Professor Bart. As you talked about privacy, actually there is also an issue of inheritance. Because of the unregulated nature of Bitcoin, that means that without the keys needed to view a relative's digital wallet, there is no way of accessing their funds if they are to pass away. So in that case, that is a kind of an issue. How do you mitigate that? And there is also a security risk, like Bitcoin exchanges. There have been cases where the Japan Bitcoin exchange that has been hacked into. So these are therefore vulnerable to hackers as well as operational glitches as well as malware. So how should that be mitigated? So these two concerns are put in front of you.
Yes, I think this is, of course, a specific problem for cryptocurrency, but of course it applies anywhere in the blockchain, because in blockchain you attach things to public keys and you have to actually take care of your private keys. But the difference with the normal banking is that, of course, if something goes wrong with your Visa card or your credit card, you can actually go to the bank and complain. And in Bitcoin, there is no place you can complain.
Right.
So you actually have to protect your private keys better. I think in that sense, cryptocurrencies are a benefit to cryptography because they encourage us to think more of how to secure keys. There is, of course, some developments in people building secure hardware wallets. And I think if you have enough money, it is worth the investment to do this. I think definitely this is a solution, just like the banks also use smart cards, which actually have quite high security. It's quite hard to crack a banking smart card. It requires you many millions of dollars to do this. It's not impossible, but there is a very high threshold. But I think one of the things that is being explored, and you may have seen this, that Coinbase has acquired last week Unbound. So what you can actually do is you can share your key over multiple places. And then you can also allocate this over multiple people. And so then you actually, if you have enough independence, if you use different technologies or different people to control this, you can distribute trust. And I guess this is what the exchanges should do as well, right? Rather than putting all their eggs in one basket, you should use a threshold system where your key is divided over multiple places. And if, say, T out of N or together, you can get your key. I mean, this is used at the Visa route. This is used at the DNS system. So this is, I also know other companies that do this. So this is something cryptography has developed in the 80s and 90s. So we know how to do this. But I guess the question is how to make this easy to use and convenient. But definitely, this is the way to go, because indeed, if you put all your keys in one place and then this computer crashes or this computer is hacked, then you lose everything. But with cryptography, the idea is you divide your secrets over multiple devices. And then, of course, if one crashes, so you also want robustness. So even if one crashes, if you have, say, 3 out of 5, you can recover the key and recover the money. It's also how you can hand over things. You can give shares to somebody else you trust. And at the right moment, you can hand them over and transfer the money that way as well. So there's definitely something that requires more research, and the problem is not the technology, it's more like how to make it usable. But so what Unbound does is using multi-party computation. So all the banks today and also the exchanges, they have hardware security modules, HSMs. They cost about $10,000. And they need many of them because they want to have a backup and so on. And they're kind of difficult to manage. And so what Unbound does is they replace this with MPC, with multi-party computation. So their idea is, rather than having one super secure device, share your key over 5 places, give them reasonable security, and you have a much more robust system that's actually easier to use and more flexible because it's software-based and not hardware-based. I hope that answers your question.
Yeah, thank you very much. And thank you for the wonderful presentation.
Thank you. Thank you very much, sir, for giving valuable time. Thank you, sir.
Thank you.
Thank you, Professor Bart.
Yes. Namaskar. Now we'll move forward to the next session. So over to Tufan.
Yes, sir.